It's called Design Trumps Analysis, drawing causal conclusions using big data very carefully. If you were looking for Donald Trump's analysis of drawing casual conclusions using bigly data, this is the wrong lecture. Okay, so I don't know where that lecture is, but this is not it. We will not be covering that today. I think that was my one joke. Okay. So what do I mean by design? By design, we're talking about study design. What do I mean by analysis? That refers to data analysis. So the theme of this lecture follows this quote by Jaz Sekon, who in 2009 wrote, "For causal inference, issues of design are of utmost importance. A lot more is needed than just an algorithm." So rather than needing just data analysis, you need to know about the study design. Oh, and the arrows are off in that slide. Okay. All right, so here's the outline of the lecture. We'll first focus on causes. We'll talk about graphs, structures, and mechanisms. We'll then talk about effects. So in the statistics literature and tradition, we talk about things like potential outcomes. So I'll go over what's called the potential outcomes framework, as well as causal inference. And then at the very end, I'll attempt to tie this into big data and those sorts of analyses. And then I'll provide you with some references. Okay, so to start, imagine, if you will, I know this is difficult in the Philippines, suppose it's raining, okay? So it's raining just like it was today. You have your umbrella with you, you take it out, and voila, it keeps you dry. So then you think, umbrellas keep people dry. Pretty cool. And you write this down on paper, and you can draw it out like this. Use umbrella, arrow, stay dry. Now, other things can help you stay dry. You can stay under a roof, that'll keep you dry. You can ride a jeepney, that'll keep you dry. These three things are sufficient causes, right? They can cause you to keep dry, but for now, we'll focus on the one that piqued our interest, using an umbrella to stay dry. So we write this, I just wrote it in small font here. Can we test this hypothesis? Well, sure. How do you test it? Use or don't use an umbrella. Record how frequently people stay dry or get wet under each condition. So the first line is what's called a causal hypothesis. The second is a causal graph. The third is you ask, can I manipulate this cause? Can I change it? And the fourth, you inquire, how can I test that causal hypothesis and then assess my analysis afterwards? This is an example of what you should be familiar with by now, an experimental study. The causal hypothesis usually takes the form X causes Y, and then we draw a graph as follows. You ask about the feasibility of testing, and then you actually design, implement, and analyze the findings of your experimental study. Examples of this for my field in public health are randomized controlled trials, and you all know those mostly as A/B testing. Now this particular graph has a special name to it where I'm from in statistics. It's called the directed acyclic graph, or DAG. I just realized I think I should be up here. Okay, so it's a directed acyclic graph. It's called directed because the arrow goes from X to Y. It's acyclic because there's no arrow that goes from Y back to X. So there's no cycle between X to Y to X to Y. It's acyclic, and then of course it's a graph. Note that your statistical analyses only come in at the end in the testing and assessment portion. All right, so we did experimental studies. Now suppose instead you examine some hospital records. This is, you're all dry and you go inside and now you look at some hospital records because you have all this free time. So why not look at some hospital records? Like I do. You notice that people treated for slip-fall injuries also tend to carry umbrellas. So you start to think to yourself, okay, this is interesting. Slip-fall injuries, maybe they increase the tendency to carry an umbrella? That seems kind of silly. I mean, why would slipping and falling make you want to carry an umbrella? It doesn't really make sense. You can't think of a mechanism behind that. So you scratch off that hypothesis. And then you think, what about carrying an umbrella? Does that increase the risk of slipping and falling? Okay, maybe. I mean, it's still a little far-fetched, but you say, okay, maybe that happens. So you examine this a little closer. What you do is you assume that hypothesis is true, that causation happens that way. carrying an umbrella causes you to slip or fall. You collect new records and you ask, is carrying an umbrella associated with more slip-fall injuries? This scenario describes an observational study. So the causal hypothesis is X causes Y, we draw it this way, but the key point here is that we're assuming the causal hypothesis is true, okay? You then collect new data, and that involves design, implementation, and analysis. And you test those hypothesized associations. Now here's another key point. Remember, we assumed the causal hypothesis was true. We assumed it was true. What we're testing is the association. When you do out-of-the-box analysis for statistical association, this is what you're testing. The analysis does not care which way the arrow goes. It doesn't know if the slipping and falling caused you to carry an umbrella or vice versa. All it knows is I'm testing for an association. The person who turned me on is the one who's assuming it goes a certain way. So that's important. And here's where the floating statistical analysis comes in. Okay, so let's look back at this example again. So what happens, let's go back. So you do that, you collect new records, you find, oh, look at that. Definitely people who carry umbrellas, there's an association with more slip-fall injuries, and I think it's causing it. Thankfully, in this case, you can actually manipulate that cause, you can test it. So you do that, you conduct an experimental study. You have like a whole bunch of people carry umbrellas or don't, and then you record whether they slip or fall. Maybe this isn't ethical, but who cares? It's data science, right? No, just kidding. In public health, there's a very strict guideline for this, and this is part of the reason you do observational studies, if it's unethical to actually experiment, right? So you conduct the experimental study, and I'm willing to bet, oh wait, sorry, like I said, you have people do that, and I'm willing to bet you find that this doesn't happen. People carrying umbrellas doesn't cause them to slip or fall more often. So then you're back after spending thousands or millions of pesos to the drawing board. Okay, well, I just spent a lot of money on that. What's going on? What if you were thinking to yourself, it was raining earlier, what if rain increases both the slip-fall injury risk and umbrella carrying tendencies? And you think, okay, well, let me draw that out. And this is what you draw. This is the directed acyclic graph, or DAG, that you draw. I've heard the word DAG has a funny meaning in Australia. Ask Isaac later. So this is a graph we haven't seen before. Now there are two arrows coming out, right? So this is an example, ooh, that skipped ahead, of what's called confounding. It's when you have one variable, in this case, I've labeled it C, that causes both X and Y. Why is it called that? Why is it called confounding? So here's a key point. If C is unobserved, so you don't know what the rainfall was like for those records, you might think that X and Y are associated, like we did, or that one causes the other, right? Which we did, contrary to fact. So contrary to the truth, this is what your data analysis told you. And so that's why we say that C confounds the relationship between X and Y, because it confuses what's going on between those two variables. And we call C a confounder. All right, so going back to the example, we ask, okay, well that's great. Can we manipulate rain? Who here thinks they can make it rain? In the literal sense, not the money sense. Money sense? No. Money sense? Yeah, maybe, some, okay. But literally, right, it's very hard, it's difficult. You can't directly or easily make it rain. Okay, let's see. So what do? We have a tool for this. It's the observational study. We assume the hypothesis is true. We collect data on rainfall and ask, is greater rainfall associated with more slip-fall injuries and umbrella carrying? And that's an observational study. Now I think I have, oops, yes. Oh, did I skip? Some slides got skipped in there. Hold on one second. Okay, so we just talked about causes, right? The title slide of this next set of slides, this is the second half of the talk, is on effects. We're going to talk about effects now. In statistics, we take this, we investigate causes that can be manipulated. Traditionally, that's what statisticians have done. They're interested in things like randomized controlled trials, where you manipulate a drug that you give people, and then you see if it has an effect. Just like Dr. Monterola was talking about. You change something, you see if something else changes. So this is the idea of causation through manipulation. One of the thought leaders in this field, Paul Holland, actually wrote, no causation without manipulation. So this is a kind of good motto to keep in mind as a guideline, especially if you are planning to conduct an A/B test, because that's what you're doing, right? You're manipulating something and seeing if something changes. So now, let's talk about a topic closer to my field of public health. Suppose you're sick. You take a drug, and then you feel better. Oh, that's nice. So you come up with this idea, the drug helps people recover. Crazy. You draw the DAG for it. You ask, can I test this? And the answer, of course, is sure. You have sick people take the drug or don't, and then you record how frequently people recover under each treatment. So I'll go through this again. Now, operationally, how do we implement this? So what you do is you randomize people. So whether you record whether or not each person recovers under the randomized or randomly assigned treatment. This is what it looks like. Most people in this room will find this nice. There's a table. Finally, he's putting a table up. First column, it's a simple table too. So the first column identifies patients, the second one identifies the randomized treatment, and the third identifies the observed outcome. So for example, patient 1 was not randomized to drug and they stayed sick, versus patient 2 who was randomized to drug and they got better, they recovered. So then it's reasonable to say, okay, I'm interested in the effect of the drug on recovery. How do I capture that? One way is to compare the proportion recovered under each treatment. And let's go through that for 10 patients. So for 10 patients, you take this simple proportion. The math doesn't get more complicated than this, I promise. Maybe there's some multiplication or something, but anyway. So we take the number recovered over the number who took drug versus the number recovered amongst those who didn't take drug. And one way to compare this is taking the difference, right? There are other ways to compare them, but that's a common way to compare numbers like these. So we do that. There are 5 people who took drug, 2 of them recovered. 5 people didn't take drug, none of them recovered. So we have this number, 2/5. How do we interpret that? We would conclude, for example, that in our sample, the drug modestly caused more patients to recover than if they hadn't taken the drug. But then you ask the people who are like really digging into this and saying, I don't know if Eric J is telling us the full story. They say, but what if each patient had gotten the opposite treatment? So what if I was randomized to drug and I got better? But what if I was randomized to the opposite treatment? No drug for me. Would I still have gotten better anyways? Would I have stayed sick? This gets into this idea that there are these outcomes that you don't observe. You only observe the outcomes corresponding to the treatment you received. So here I've laid them out for each patient, and I've boxed them. Because these are outcomes that are potentially observable, we call them potential outcomes. You see here, ooh, that got messed up. But the point of this slide was to show you that you see only the outcome that corresponds to your randomized treatment. So in a way, these observed outcomes are, in a sense, a sample. They're a sample of the population of potential outcomes that you're actually interested in if you take this approach, right? And you want to infer something from what you can see in that sample. You want to infer something about all of the potential outcomes. This is a good point to stop and review inference. So what do we mean by inference? Statistical inference, hopefully this is a review, is the concept of taking a sample and inferring or deducing properties about a much larger population that you don't see, right? There are 3 components usually. One involves statistical modeling, and that just is the process of applying mathematical functions to probabilities and the relationships between variables. Then you want to estimate certain things like parameters or sometimes entire distributions. And then finally, you want to test to see how good is your sample. Is it big enough to say that that estimate accurately reflects or represents what you're after? So this is a talk about causal inference. So what's the difference between that and causal inference? Spoiler, before I click the next button, can anybody tell me what the difference is between causal inference and statistical inference? I'll give you a hint. The last two things are the same. No? Okay. The difference is in causal modeling. So two of those parts of statistical modeling, mathematically describing probability and the relationships between variables, stay the same. The third is that you now layer on causal assumptions on top of that. And this has to do with what we covered in the first half. You're supposed to see it was half, but the slide is gone. But the first half on causes, right? We were talking about the causal relationships and what we were assuming they were like. That's the difference. The two other parts are the same. But of course, this is a big data talk. So how does big data fit into all this? Because it's chewing gum and staying dry are not even associated. Yeah, I'm going to stop myself from thinking of some weird comic book way to justify it. But so that's the tie-in. That's one of the overlaps with big data analyses and predictive modeling. Or predictive modeling is one of the big overlaps. So let's very quickly review what we just covered, and I'll throw up where big data fits into each of these. So for causes, we looked at causes. We talked about graphs, structures, and mechanisms. We talked about experimental studies and directed acyclic graphs, or DAGs. We reviewed observational studies, and we were introduced to confounding. When we looked at effects, we went over the potential outcomes or counterfactual framework, and we talked about causal inference, as well as reviewing the concept of statistical inference, which was necessary to understand causal inference. We talked about potential outcomes and discussed the average treatment effect. And finally, we talked about adjusting for confounding, a very powerful suite of methods. So big data, from what I understand, again, I'm still trying to get into it, falls into place mostly here. See, these aren't black and white designations, there's overlap, but this is where they really shine, right? I just showed you a DAG. Basically, I took the arrows away and I showed you how prediction works in that setting. Prediction's used a lot in machine learning. It's one of the mainstays, as well as data mining. Of course, that was an observational study I showed you, and confounding is just a property of different relationships on a DAG. A/B testing, of course, you're experimenting, so it has to do with experimental studies, as well as inference, because remember, that's the power of randomization. Getting at the population of potential outcomes and estimating something about them, and then doing that by defining the average treatment effect to talk about in a smart way, the effect of a cause. More recently, machine learning and data mining methods are being used for adjusting for confounding. This is where I hope to network with some people, because I'm trying to do this for my own work. And yeah, please come talk to me afterwards. It's super exciting. I start freezing up when I think about it. I mean, not like here. Well, no, yeah, here too. Okay, so both head and heart. Okay, so do I still have time, or, yep, still time? Okay. All right, so very quickly, I'll go over what's called explanation versus prediction. There's an article that I encourage you to check out. You don't have to necessarily read it. It's a short article, not super technical. It's written by a statistician about her views on data science and statistics and where they overlap and where they don't, and how they're useful for each other, and how they go in different directions. It's this article, I'll throw this up again at the end in the last slide, by Galit Shmueli, called To Explain or Predict. Notice her first name is Galit. Wait for it, yeah, wait. So my hope is when you read this article, hindi nakakagalit, pero nakakagulat yata. Because she talks about the differences and the overlap. Traditionally, there's kind of a rivalry between statistics and data science. So she defines explanation as this. 3 more slides, I promise. 3, 4, 5 more slides. I define explaining as causal explanation and explanatory modeling as the use of statistical models for testing causal explanations. That's explanation. Prediction. I define predictive modeling as the process of applying a statistical model or data mining algorithm to data for the purpose of predicting new or future observations. She has a little more text here where she discusses statistics versus MLDM. In fact, the differences in some would say rivalry between the fields of statistics and data mining can be attributed to their different goals of explaining versus predicting, even more than to factors such as data size. She talks about effects and causes. I'll skip past that. Population versus sample, inferences versus predictive power. The point is that statistics tends to focus on inference to a target population, whereas data science, data mining, and machine learning tends to focus on predictive power. They're related, but they're not exactly the same. Because sometimes a variable can be very statistically significant and not predictive. So the kinks need to be worked out. But there's a good potential for overlap. And she even says, statistical significance plays a minor or no role in assessing predictive performance. And finally, she says, explanatory power and predictive accuracy are different qualities a model will possess some level of each, which is a big take home for all of us. All right, so here are my references. A little short plug for my own work. I have an article currently accepted at Methods of Information in Medicine. So I'm a postdoc, so I'm at the start of my career. I'm trying to throw my stuff out there. But if you're interested, my research focus is causal inference on single subject analysis. So in public health, that's literally a single subject or a time series. Those methods are what I've been tapping into. And I'm a newbie at time series, so this is really exciting and really hard for me. I know causal inference, I don't really know time series. It'll be published in November, December. It's open access, so it'll be free. But the use to you for this, even if you don't really care for the article, is in the online supplement, I have a list of causal inference literature for the topics I covered today. There are lots of really good survey articles out there, but if you look at that supplement, there's just a list of various ones that'll get you started. So hopefully you find that helpful. So that's it. I had a last slide. Just wanted to say maraming salamat po, thank you kindly. And I will leave you with, promise this is it, the last one. Don Rubin is one of the preeminent developers of causal inference in statistics. And he said that for objective causal inference, design trumps analysis. Thank you.